Good day everyone. In continuation to our lecture with module number 8, the solution of ordinary differential equations using initial value problems. We are already done with the Euler's implicit and explicit method together with the modified Euler's method. This time we move on to the Runge-Kutta method. With the Runge-Kutta method gives a more accurate solution compared to the simpler Euler's explicit method. The accuracy increases such that the truncation error also decreases. So basically, we have already decreases the errors committed with the Euler's explicit and implicit method and using the modified Euler's method. But with the Runge-Kutta method, we would still decrease that error by also increasing the order of the Runge-Kutta method. Speaking of the order with the Runge-Kutta method, there are two orders of the Runge-Kutta method. First up is your lower order of the Runge-Kutta method, and the second one would be your higher order of the Runge-Kutta method. Under the lower order of the Runge-Kutta method, we have your first order differential equation and the second order Runge-Kutta differential equation method. But you are already familiar with that. You are already familiar with the first order differential equations. So we move on with the second order Runge-Kutta method. With the second order Runge-Kutta method, its general form shows that the value of y sub n plus 1 should be now equal to the initial value of y or y naught plus the constant value of c1 times the computed value k1 plus the constant value c2 plus k2 times the adopted step size to ensure the accuracy of the answer, which is your h. But in relation to our lecture from previous meeting, you will then apply this formula with the modified Euler's version. So its modified Euler's version, the y value of y sub n plus 1 should now be equal to y naught plus h over 2 step size, h over 2, times the computed value k1 plus k2. Using the general formula for the second order Runge-Kutta method, we can then compute for the value of k1 as equal now to the function of x naught and y naught, and the value of k2 should then be equal to the function of x naught plus the step size plus the constant value a2 times the step size, and y naught plus b21 k1 times the step size or the computed value k1. These are the general form for the second order Runge-Kutta method in computing for k1 and k2, where the c1, c2, a2 and b21 are constant values. The values of these constants vary with the specific second order method on differential equation. But with that regards, we will then only be using the modified Euler's version. With the modified Euler's version of the second order Runge-Kutta method, the k1 should then be computed as equal now to the function of x naught, parehas pa rin naman sila, and y naught, and k2 is now equal to the function of x naught plus the step size and y naught plus k1 times the step size. Okay, we will then be removing the constant value by under the modified Euler's version. Okay, so we will be using the modified Euler's version on the second order Runge-Kutta method. Okay, we will be using this one or these formulas for the second order Runge-Kutta. By doing so, let's move on to an example problem under the second order Runge-Kutta method. Okay, so for our example problem, for the second order Runge-Kutta method. So for your example problem under second order Runge-Kutta method, using the second order Runge-Kutta method, modified Euler's version, to solve the ordinary differential equation dy over dx equal to negative 1.2y plus 7e raised to negative 0.3x from x equal to 0 to x equal to 2 with the initial value of y equal to 3 and x equal to 0 using a step size of 0.5. So basically we're being asked for the value of y at x equal to 2. By doing so, the initial value on this problem was given as x naught equal to 0 and y naught is equal to 3. Using a step size of 0.5, we are now asked to solve for the value of y at x equal to 2. Okay, with that said, we will then have to set our iteration based on the given step size. For our iteration, okay, and the value of x plus the step size, and the value of y equal to y naught plus h over 2 equal to k1 plus k2. Remember, we are using the second order Runge-Kutta method using the modified Euler's version. So for the first iteration, the initial value was given as equal to 0 and y naught is equal to 3. The second, 0 plus 0.5 is 0.5. The third is 0.5 plus 0.5 is 1. The fourth, 1 plus 0.5 is 1.5. And the fifth iteration is simply the value of x equal to 2. We are now asked to solve for the value of y at x equal to 2. Okay, so we need first to solve for the value of y1, y2, y3, and lastly, of course, for the value of y4, which is our unknown. Okay, by doing so, let's move first for the value of y1. For the value of y1, simply that is equal now to the y naught plus h over 2 times k1 plus k2. So remember that dy over dx is simply equal to negative 1.2y plus 7e raised to negative 0.3x. That the k1 is then computed by the function of x naught and y naught. Then we know that from our initial value, or x naught and y naught, x naught is equal to 0 and y naught is equal to 3. So basically, we were only substituting 0 and 3 to our equation there. So negative 1.2 times 3 plus 7e negative 0.3 times 0. So basically, k1 is now equal to 3.4. Same goes with k2. Remember that the function for k2 for the general form of second order Runge-Kutta method using the modified Euler's version is x naught plus h and y naught plus k1 times h. So by doing so, that is your x naught plus h and y naught plus k1 times h. Substitute lang natin lahat ng known values. X naught was identified as 0 plus step size of 0.5 and y naught is 3 plus k1 of 3.4 times the step size of 0.5. Okay, so we will then be able to solve for k2 as the function of function of 0.5 and 3 plus 3.4 times 0.5, that is 3 plus 3.4 times 0.5 is simply 4.7. Substituting that to our equation, K2 is simply equal now to negative 1.2 times 4.7 plus 7e raised to negative 0.3 times 0.5. So K2 now is equal to 0.385. Okay, as much as possible, try to use a much higher number of decimal places on your own computations and with your further quizzes and exams and calculations para mas accurate yung answers ninyo. But for now, I'll be using 3 decimal para mas mabilis yung ating lecture. Okay, then we already know the value of K1 and K2. We have Y0, we also have your step size. So we'll now be able to solve for the value of Y1, which is Y0 is simply 3, step size of 0.5 over 2, then K1 is 3.4, and K2 is 0.385. Gives us the value of Y1 as equal to 3.94625 at 25. So yan na yung ating Y1, which is 3.94625. Okay, now in continuation, we will now be able to solve for the value of Y2. For the value of Y2, for Y2 simply equal to Y1 plus the step size over 2 times K1 plus K2. Okay, again, dy over dx is still equal to 1.2 times y1 plus 7e negative 0.3 x1. Yeah, x1. So, remember, computation ulit tayo. K1 is equal to f of x1 and y1. Ano yung value ng ating x1 and y1? x1, 0.5. y1 is 3.94625. Okay. So, that is basically equal now to f of 0.5 and y1 of 3.94625. Basically, substitute lang natin yan sa equation. Hindi ko na ilalagay. Kayo nang bahala mag-substitute. So, we'll have the value of K1 as equal to 1.289456. Okay. Then, for the value of K2, K2 is f of x1 plus h of y1 plus y1 plus k1h. So, simplify lang natin. x1 is 0.5 plus h of 0.5. Then, y1 is 3.94625 plus k1 of 1.289456 times 0.5. Okay, you can simplify that as x equal to 1 and y is equal to 4.590978. Basically, again, substitute lang natin yan doon sa ating equation. K2 will then be equal now to negative 0.3234446. Okay, so meron na tayong K1 and K2. Again, we can simply solve for y2. y2 is y1, which is 3.94625 plus the step size of 0.5 over 2, K1 of 1.289456 9496 plus K2 or minus 0.323446. Simplify on your own, gives us the value of y2 equal now to 4.187753. So we can now immediately use that y2 to our table. Is 4.187753. Yeah. Okay. So, continuation, solve naman natin si y3. So, for the value of y3, that is equal to y2 plus the step size over 2 times k1 plus k2. Again, dy over dx is equal to negative 1.2y plus 7e raised to negative 0.3x. So solving for k1 again is equal to the function of x2 x2 and y2. So k1 is then equal to x2. Ano yung x2 and y2 natin? x2 is 1 and y2 is 4.187753. x2 is 1, y2 is 4.187753. Then immediately substitute that to your equation, gives us k1 equal to 0.160424. Then for k2, that is f of x2 plus h and y2 plus k1 k1h. So x2 is 1 plus 0.5 and y2, which is 4.187753 plus k1 of 0.160424 times 0.5 gives us k2 function of 1.5 and $4.267965. Substitute that again to your equation, gives us k2 equal now to negative 0.658161. So by doing so, we can simply substitute that to our equation for y3. Solving for y3, y2 was 4.187753 plus h of 0.5 over 2 times the computed value of k1 and k2 of 0.160424 minus 0.658161. Computing or simplify, y3 gives us the value of 4.063319. So yan na po yung ating y3. 4.063319. Continuation, we can now immediately go in solving for the value of y4. For y4, which is at the value of x equal to 2, which is our unknown, yan na yung pinaka last na natin kailangan i-solve. y4 is y3 plus h over 2 times k1 plus k2. Again, using the same equation, k1 is equal now to f of x3 and y3. So k1 is equal to f, x3 is 1.5, y3 was computed as 4.063319. So k1 is now equal to negative 0.412586. So yan lang naman yung hinahanap natin dyan. So for K2 under Y4, K2 is basically f of x3 plus h of y3 plus k1 times h. Direct substitute ko na po, kayo na maglagay sa inyong calculator. So the function of x now is 1.5 plus 0.5, that is 2. Then for y3 plus k1h, y3 4.063319 plus k1 of negative 0.412586 times 0.5. That is 3.857026. Substitute to our equation, to our given function. Substitute lang natin dyan. K2 for y4 is negative 0.786750. Now we can then immediately solve for y4. So y4 is equal to y3 of 4.063319 plus h of 0.5 over 2 times k1 of negative 0.412586 minus k2 0.786750, which give us the value of y4 is equal now to 3.763485. Okay, and that will serve as our final answer to the requirement of this problem, which is the value of y at x equal to 2. Yan na po yung ating answer. Okay, ito yung ating answer. Lagay lang natin dito. So for y4 at x equal to 2, that is now equal to 3.763485, which will serve as our final answer. So with that serves as our second order Runge-Kutta method. Next lecture we'll move on to the higher order Runge-Kutta method, dealing with the third order and the fourth order Runge-Kutta method and their equivalent modified Euler's version. So I'll see you on the next lecture video. Bye bye.